In mini lecture 26, I want to do a little recap. I want to essentially go at 20,000 feet and see how do we approach second order circuits, the kind of things that you should think the minute that you get a problem. You should have that in the back of your mind in terms of how you are approaching the solution to the problem. And then I'm going to basically set up one last example. I'll get down to the general solutions, the differential equation, the general solution. We'll use mesh to do this, just to put all this thing to put it in perspective and in context. Okay. So first I'm going to start a recap, and the recap will be two-part, by the way. I'm going to do a recap looking at more the circuit end of things, and I'll do a little bit of a recap of the differential equations, that part of your differential equation course that relates to what we're doing now. Okay, so let's go to the document camera and begin a recap. Okay, so we are looking at, let's do a recap of, again, our circuit analysis. So what are we doing here? We're solving second order circuits. Okay, and what does that mean? That means two energy storage elements in general. And these energy storage, the energy storage elements are the inductors and the capacitors, which we're calling L and C's here. Okay, so the solution to that circuit generally leads to a second order differential equations. Which we will refer to as ODE. Okay, so that's the first part here, things that should come to your mind here. We are solving circuits that are excited by DC or constant sources. With switches. Okay, switches that are either closing or opening up, but the switch is causing a change in the circuit here. So things that you should note here is we solve the circuit before the switch action. And we solve the circuit after the switch action, after the switch move. Okay, so that's really important. And we do so sequentially. Sequentially. We solve for the first time period first, then for the second time period. Okay. The first time period gives us our initial conditions. Okay, so that's why we need to essentially solve for that. And during the first time period, again, we're looking at a constant source circuit. So that means the capacitor behaves like an open, and the inductor behaves like a short, a wire. Okay, so when we solve for the first time period, we are looking at a DC circuit we're not looking at the capacitor is not present and the inductor is not present either. That's important to notice that, okay? So finally, let's talk about initial conditions. Of course, we get our initial condition from the first time period. Okay, that's what we get it. And regardless of what you are being asked in the circuit, the initial conditions needs to be calculated: capacitor voltage, and inductor current are the initial conditions. In other words, regardless of what I ask you, you always need to calculate the capacitor voltage and the inductor current. Okay, I could ask you something else. You need to calculate these two because they are the initial conditions. Why are they the initial conditions? They relate to the energy stored in those elements. Okay, they're really the energy stored. I've used the gas tank analogy quite a bit. That's the inductor current and the capacitor voltage. You can think of they are being related to the energy stored in this. The energy is the initial condition for these elements. Okay, so I'm hoping this is actually a pretty good summary of the key points that you need to be mindful when you get a second order circuit, in essence, there. Okay, so now I'm going to do essentially a what I call ordinary differential equation, ODE recap. Okay, this is kind of a Math 45 if you're at Sac State or if you're at other institution. You may have another. If you get your differential equation from someplace else, you may have a different a different number. All right. So we again, when we talk about differential equation, we are talking about at least the second time period once the switch has moved. So I'm going to say that once the switch has moved. For the simple reason that, again, in the first time period, the switch had not moved yet. The capacitor behaves like an open and the inductor behaves like a short. You're looking at a DC circuit, a resistive circuit with sources. If the sources are constant, then the capacitor is not behaving like a capacitor. The inductor is not behaving like an inductor. So we are solving differential equation that look like this. I'm purposely using X, okay, instead of voltage or current because it can be voltage or current. 2 alpha dx dt plus omega n squared x equals some constant C1. That's essentially the differential equation we construct. Second order, constant coefficient, everything is constant, alpha is constant, omega n is constant, and C1 on the right-hand side is constant. We've just far looking at the case of the right-hand side being 0, but today we're going to see an example where the right-hand side is not 0. Okay, so I wanted to essentially broaden a little bit that discussion, bringing in your differential equation content before we do the example here. And we essentially, once you get this, no proof is required on my part. I don't need you to prove that. Identify, what I want you to do essentially is identify alpha and omega n, okay? So alpha is essentially the constant associated with the first order divided by 2, and omega n is the square root of the constant associated with x, okay? Then you proceed to tell me which case that we're dealing with here. So case 1, okay? Case 1 here, it's what we call the overdamp. That is alpha larger than omega n, okay? That's case 1. In the case 1, essentially, we're looking at x of t is equal to a e to the s1t plus b e to the s2t plus c1 over omega n squared. Okay. So this is what we call the natural response And this is what we call the force response. What your Math 45 calls was the complementary. And this was called the particular. We in electrical engineering has to have different term for these things, but they are the same concept here. And S1 or S2 is minus alpha plus or minus square root of alpha squared minus omega n squared. Okay, so one of them is the plus, the other one is the minus. Okay, so that is case one in terms of your Math 45 or differential equation content. And that is what we call the overdamped case. The overdamped, essentially, what you get, essentially, you get two real numbers for S1 and S2 that are negative but real. So two negative numbers. So you're looking at two exponents that are dying out, the exponent quickly dying out. That's what this is called, the overdamp. It dies out. Okay. Case two, by the way, case two and case one are the most, it's called the underdamp. And this is the case where omega n is larger than alpha. Okay. Underdamp. Okay. This is kind of the oscillation here. Okay. So what we got in case two and case one, we got x of t is equal to e to the minus alpha t, a cosine square root of omega n squared minus alpha squared t plus b square root of, sine, it's in the sine, omega n squared minus alpha squared times t, okay, close bracket, plus C1 over omega n squared. You still have the force function, the force response here, which is the old particular, and this is the natural complementary response. Here again, don't forget the sign that I'm missing here. Okay? So that's case two. These are the two most important cases, essentially. So what you have, this is what I call the general solution. General because constant A and B are not determined yet in both cases. These are determined via the initial conditions. Okay. And then finally, case three, which is a much less interesting case, it's called the critically damp case. It's the double root alpha equal omega n. So x of t is equal to a e to the minus alpha t plus b times t e to the minus alpha t plus c1 over omega n squared. Okay, this is a critically damped case, much less important. Generally, you have to tune a circuit to get there. The case one and case two are the dominant and most important case in real life. Okay. So this is actually a good summary of your second order content, second order differential equation content that pertains to Engineering 17, pertain to the circuit analysis course. These are the things that your course in differential equation has looked at that very early. So it's not like something that's complicated. Again, no need to prove any of that. I need you to identify for me, once you get the differential equation via nodal or mesh, identify alpha, identify omega n, tell me which case we're dealing with, and write the general solution. And then, so once you do that, then the remaining step is to use initial conditions to calculate the constant A and B in each case. The constant A and B are found from the initial conditions on the capacitor voltage and the inductor current from the previous time period. Okay, so I'm hoping this is a kind of a circuit recap of key points in the circuit. This is a recap of your differential equation course content that pertains obviously to circuit analysis that we are doing right now in the second order part of circuit analysis, obviously. So now I'm going to look at a particular example, and we're going to somewhat put all of this in practice. Of course, we'll have only one case. We won't have all three cases, but these content, this particular will be quite timely in that. So let's look at the example that I have. So this is the circuit that I will going to solve here. This is asking to calculate the current to the capacitor IC for all time. Okay, so what you have here essentially, this is again part of the discussion we were having here. You have a circuit that has all DC sources. There's a 4 milliamp current source, so it's a source that's not changing, but you have a switch that opens up. The switch is actually closed, and at t equals 0, it opens up, disconnecting that 0.1 ohm resistor. Okay, so part of the discussion we were having again so we have we're going to solve the circuit for 2 time period for t less than 0. So what do we have here? We have the 4 milliamp, 0.1 ohm. Again, the inductor behave like a short circuit, a wire, because everything has been constant for a very long time. The switch is closed, so that other resistor is connected. And then the 0.52. And then the capacitor again behave like an open. Okay, so that's the circuit we have here. And if you follow my discussion on the previous paper, the recap we were doing here, even though I'm only asking you to calculate the current IC, I need the capacitor voltage. I'll call it VC. I also need the current on the inductor, which I'm going to call I1. Okay, I need that current because that current and the capacitor voltage are my initial condition. It doesn't take a whole lot of thinking to appreciate that IC is 0 here, because obviously the capacitor essentially is an open, so there is no place for the current to go. And if the capacitor, this current is 0, that means there is no voltage drop under 0.52 ohms. So actually the capacitor voltage is also here. Okay, so that's the first thing. And then you end up having, what do we have here? We have a current source feeding 2 equal resistors. So we can use current divisions to get I1. So I1 is just 2 milliamp. That's the inductor current again. And then we can get the capacitor voltage that's equal to I1 multiplied by 0.1. So it's 0.2 millivolt. Okay. So these two things are my initial conditions. Okay. Even though you were asked only for the capacitor current, I needed to calculate these two. Now you can put your polarity of your voltage however you want. You can put your current direction on the inductor however you want if it's not given, but you need that. So this is the kind of, as I say, this is putting context to the recap that we were just doing here. And it's important to see it in action, if you will, as opposed to somewhat a series of statements here. So next, I am going to look at t greater than 0. Obviously, at t equals 0, this thing opens up, disconnect that 0.1 ohm. So what do we have? So the inductor now is back. That's it. Okay, so that's the circuit we have. The switch opens up, disconnecting this resistor. The inductor and the capacitor are back because the switch motion made a change that somewhat wakes them up, if you will. Because of that change, that essentially they no longer behave as open and short. So we have this here. And I'm going to proceed to set up a mesh analysis procedure. Okay, I'm going to set up a mesh analysis procedure so that we can essentially solve this circuit. My hope is to come up with a differential equation using mesh, then write the general solution. I'm going to leave the calculation of the initial condition constant to you, but I will show you how we do this. Okay, I will essentially guide you on that here Okay, so let's begin our step here. So there is I1 here. By the way, I1 is, and then there is I2. Okay, I1 is our original I1 here. In this particular case, was the current to the inductor. It's also IC. Okay, I'm going to put voltages on my element here. Of course, the capacitor already has a voltage, so I don't add another voltage to it here. So I'll prepare the circuit for a mesh solution. Okay, so whenever we talk about mesh, I want to take a few minutes to talk about how we do mesh for circuits here. Anytime we do mesh, we need to pay attention to current sources. We need to pay attention because we need to write one source equation per current source. All right, that's what I'm going to do. All right, and then we need to note where the current source is. Is it in one mesh or is it in two meshes? When it is in one mesh, we only write the source equation. When it is in two meshes, we need to do also a KVL about the super mesh. In this case here, it's on one mesh, so we only write the source equation. And when we say source equation in mesh, we're essentially writing the current source in terms of the mesh currents. In this case here, the current I2 must be equal to 4 milliamp. That's it. That's an easy equation to write. Okay, that's our source equation for this. And then I have one mesh now that I'm going to do KVL here. Okay, so the step you're seeing me, it's what I expect. That's how I grade your work. I want to see this organization in your work here. So let's separate this out a little bit. So first step here, I'm going to do KVL in mesh I1. Okay, so what do I have here? I have minus V1 plus V2 plus V3 plus VC equals 0. I'm going to call this equation 1 because this equation is pretty final, so I call this one equation 1. That's my KVL in mesh I1. Okay, I do KVL in terms of voltages. I expect you to do the same thing. Then I write Ohm's law for all my resistors. Often I'm going to call Ohm's law OL. Okay, so Ohm's law, V1 is 0.1 times I2 minus I1. And then for the 0.52 ohms, so V3 equal 0.52 I1. Okay, that's the ohms. Then I basically do KVL plus Ohm's law. In other words, I bring the Ohm's law equations into all my KVL. Now, I get it that I have only one KVL equation. The process is the same if you had 3 KVL equation or 2. Okay, so equation 1 then become minus V1, which is minus 0.1 I2 plus 0.1 I1 plus V2 plus V3 plus 0.52 I1 plus VC equals 0. Okay. All right. So what I'm going to do here, I'm going to say this, I'm going to eventually use the value 0.2, 4 milliamp for I2, sending on the other side, and I'm going to collect the terms. I'm going to collect the term for I1 here. So what do I have here? I have 0.62 I1 plus V2 plus VC equal 0.1 times this. So it's essentially 4 times 10 to the minus 4. Okay, that's what we got. Okay, so this is again my step KVL plus Ohm's law. Then I'm going to write the capacitor and the inductor relationships. For the capacitor, what is the capacitor relationship? The current to the capacitor is I1 is 10 over 18, the derivative of the voltage. For the inductor, what's the current to the inductor? What's the voltage? The voltage is V2. So V2 is equal to 0.05 d I1 dt. That's my inductor relationship. Anytime you write this relationship, you have to, of course, you have to know this relationship, but ask yourself, what is the capacitor voltage? What is the capacitor current? What is the inductor voltage? What is the inductor current? And write this relationship. Now I'm going to bring them into this. So this step is KVL plus Ohm's law plus capacitor and inductor. Okay, that's that step that I would call that. So first I'm going to bring the inductor. So this is equation 1, by the way. So equation 1 becomes 0.62 I1 plus 0.05 di1 dt, okay, plus Vc equal 4 times 10 to the minus 4. Okay, so when I mean bring in, wherever I have V2 in this relationship here, I only have it in one place. I put 0.05 di1 dt. That's what you get there. Then now I'm going to bring in the capacitor relationship. So wherever I have I1, I'm going to put 10 over 18 derivative of voltage. So I have I1 here and I have I1 here. This is going to give me a second order derivative. So I1 here, so 0.62 times this. So I get 0.62 times 1018 dVc dt, okay, plus 0.05 times 1018 second derivative of voltage with respect to t squared, okay, plus Vc equal 4 times 10 to the minus 4. Okay, I'm basically almost there. I have to basically normalize and essentially write the standard differential equation. I could actually multiply this entire thing by 18. So what do I get? I get 6.2 dVc dt plus 0.5 second derivative of Vc with respect to t squared plus 18 Vc equal to, let me get my calculator here. 7.2 times 10 to the minus 3. How's that? Okay. The only thing I have to do essentially now is divide by 0.5. The standard differential equation that we deal with is one that the highest order derivative has a unit coefficient. So I can divide the whole thing by 0.5. So what do we have? Second derivative with respect to t squared. Okay. Plus that's our differential equation. That's our differential equation in the standard format, okay? So you've seen essentially how I come across this, the standard process here. Once I get the second time period, the inductor and the capacitor are back, I essentially begin a normal mesh analysis approach, source equation, then I go KVL in the mesh that don't have current sources. And then Ohm's law, bring in the Ohm's law, that's the step, KVL plus Ohm's law. Then I write the capacitor. I want to write them separately. When I do this thing here, you need to be mindful of the passive sign convention. Because remember, these elements are passive elements, okay? You need to be mindful of the passive sign convention. That is the current entering the voltage on the positive terminal. So we write this. And then now this step is KVL plus Ohm's law plus bringing the inductor and the capacitor. I bring the inductor first, and again, and then I bring the capacitor, and that picks up a second order derivative there. And then the last step is to normalize. Okay, at this point here, what I need you to do for me is identify alpha. Alpha is just this coefficient divided by 2. So alpha is 6.2, and omega n is the square root of this coefficient, which is 6. So alpha is larger, so this is an overdamped case. This is the overdamped case. You're going to need to calculate S1 and S2 and then write the general solution, essentially. So keep in mind here that the capacitor relationship here, the capacitor current is also the inductor current, because we're going to need this relationship to enforce the initial condition here. So I can calculate again, looking at S1, S1 is minus 6.2 plus square root of 6.2 squared minus 36. Okay. And that's minus 4.64. And then S2 is minus 6.2 minus square root of 6.2 squared minus 36. And that's minus 7.76. Okay. So the solution for VC, the complete solution, all right, it is A e to the minus 4.64 t plus B e to the minus 7.76 t plus the force response is this divided by 36. And if I did my math, it is plus 4 times 10 to the minus 4. So that is the general solution for VC. The work that's being done essentially is to use this relationship here and the current to the inductor, because the current to the inductor is also the current to the capacitor. So you would need to do this. You would need to work up the derivative and then multiply by to get the current to the inductor, which is the current to the capacitor. And then we would enforce these two things here. We would say I1 at 0 is equal to 2 times 10 to the minus 3. And VC at 0 is equal to 2 times 10 to the minus 4. Those are the two initial conditions that you essentially would have. Okay, let me see if I can do a little bit of zoom here. No. Okay, so these are the two initial conditions that we would have that would give us equations for A and B to solve what we would need that. I think I've done enough to get you going. I'm hoping that last step, your differential equation course and basic algebra helps you get there. But this general solution is a great step. You would need to get I1 by takes the derivative of this and multiply it by 1018 and then enforce this. That gives you two equations, two unknown for you to work with. I hope that helps.